You ever wonder what's really going on inside an AI's head when it solves a tricky problem? I mean, it can seriously feel like magic, but researchers are starting to crack the code, showing how even simple AI models can learn to think things through step by step. So let's dive in and see exactly how they pull it off.
So here's the big question we're tackling. How do models like ChatGPT actually go from a complicated question to a logical, step-by-step answer? You know, they're not just regurgitating stuff they've memorized, there's an actual process happening in there, and figuring out that process is one of the most exciting frontiers in AI research right now.
Okay, so the key idea here is something called chain of thought, or COT for short. It's basically a technique where you prompt an AI to think out loud. It's like when you had to show your work in math class, it breaks the problem down into smaller, simpler steps before spitting out the final answer. And what's wild is that just having it do this can massively boost its accuracy on really tough problems.
So, to really get to the bottom of this, researchers had to strip away all the complexity of human language. They needed a clean, controlled experiment. So they designed what's called a toy problem, which is a perfect way to isolate the pure mechanics of reasoning, step by step.
And this is their laboratory. The task looks pretty simple, right? Just find the path between 2 points, or nodes, on this tree. You can see the goal is node 8, and the starting point, the root, is node 4. This little puzzle is actually a perfect stand-in for pretty much any problem that requires a logical sequence of steps to solve.
Now, this is where it gets really clever. The researchers actually set up 2 versions of this task. The easy one is backward reasoning. You start at the goal, node 8, and work your way back to the root at 4. That's a piece of cake, because every node only has one parent. There are no wrong turns. But the hard version is forward reasoning, going from the root down to the goal. At each fork in the road, the model has to make a choice. It's super easy to take a wrong turn and get lost.
Okay, so this brings us to the first huge breakthrough in this research. You'd think you'd need this giant, super deep neural network for a task like this, right? Well, the researchers proved that a surprisingly simple, one-layer transformer model could be built to solve not just the easy task, but the hard one too.
All right, let's start with the easy one, the backward task. It's actually pretty straightforward. The model starts at the goal, let's say node 8. It has a single attention head, you could think of that as its focus, which looks at all the connections to find the parent, which is node 1. It then outputs 1 and just keeps doing that, step by step until it hits the root. Simple enough.
But that brings us to the million-dollar question. That forward task is loaded with dead ends. So how on earth does this simple, one-layer model solve the hard problem without a map? How does it possibly avoid getting totally lost?
And this is where we see the second big innovation. And honestly, it's just brilliant. They designed a system with 2 specialized attention heads that work together like a team. You've got head 1, the pathfinder, whose job is to actually move along the tree. And then you have head 2, the stage manager, and its only job is to tell the pathfinder which way to go.
So the solution is this really elegant 2-stage process. Check this out. To solve the hard forward problem, the AI first solves the easy backward one. So in stage 1, the stage manager is basically holding up a sign that says, go backwards, and the pathfinder traces the path from the goal all the way back to the root. But then, and this is the turning point, once it gets to the root, the stage manager just flips its sign all by itself to go forward. And now all the pathfinder has to do is read the path it just created, but in reverse. Boom. Perfect root-to-goal solution.
Okay, I know what you're thinking. This sounds like a really neat trick that a human designed, but can an AI actually learn to do this on its own just through training? Well, let's look at the proof.
The proof is right here in these charts. These graphs show the model's error rate, its loss, during training. For both the easy backward task and the way harder forward task, the loss just craters down to basically 0. And importantly, that includes the test loss on brand new trees it's never seen before. I mean, that's a home run. It proves the model didn't just memorize answers, it learned the actual reasoning mechanism.
But wait, it gets even cooler when you look under the hood. This graph shows what's happening inside the model as it trains. You see this green line? That's the model strengthening the connections for the right path. And the red line? Those are all the wrong turns, and the model is actively learning to just ignore them. It perfectly converged on the exact solution the researchers had designed.
And the researchers themselves put it perfectly. They said, this reveals an appealing insight. The transformer learns a rule for pathfinding rather than memorizing training examples. In other words, it's not just parroting answers, it's actually learning the fundamental skill of reasoning itself.
So what's the big so what here?
What does this super simple experiment tell us about the future of AI? Well, the implications are actually huge, and they all circle back to one very simple, very powerful idea.
So let's just recap the big innovations we saw. First, a really simple, shallow transformer can tackle these complex, multi-step reasoning problems. Second, different parts of the AI, these attention heads, can learn to specialize and work together on different parts of the problem. And maybe the most important piece of the puzzle, the real key was generating that intermediate path to use as a kind of mental scratch pad.
And that right there is the big idea. The magic here wasn't about making the model bigger or deeper. Nope, the power came from using the output of a simple process, finding that backward path as a scratch pad to solve a much harder one. This suggests that the length of the reasoning process, that chain of thought, could be just as important, maybe even more important than the sheer size of the AI model.
And all of this leaves us with a really fascinating question to chew on. Is the race for better AI really just about building bigger and bigger models? Or is the real frontier about designing smarter, more elegant, and more efficient thinking processes for our AIs to use? This research certainly suggests it might be the latter.